So we looked at the data centers in terms of how they are built and what are the core components. Now, when we consider the networking part of the data centers, we have to consider many other aspects in terms of how the networking is laid out and what are the challenges that we should be addressing when we are trying to deploy the networks for data centers. So primarily, we spoke about different kinds of applications that these data centers support in terms of the e-business applications. Like, for example, consider Amazon as a website and you see a host of applications that they provide. And likewise, the content service servers or content service providers, the Akamai, etc., facilitate for shipping multiple of the web servers onto their domain and facilitate connectivity from nearest possible location. Likewise, for the contents you see as YouTube, Microsoft services, and even the search engines, etc. So, myriads of applications, not just the web servers, but also the content. Some are, say, latency sensitive, some are throughput sensitive. All kinds of applications exist on the network that are being facilitated through these data centers. Hence, the foremost of the challenge that we would also need to think in terms of first is how to scale, enable the scale for multiple applications where each is serving massive number of clients. That means the network should not be a bottleneck in facilitating the requirements of connecting multiple users, or in terms of if it translates to network, it is equivalent to saying large number of flows. And when we say multiple of data, maybe database servers, data like streaming servers that are going to be accessing the data, the scale also means in terms of the bandwidth that we would want to support. Again, the second aspect is the performance, where if there are multiple of the servers that are serving similar kind of content, how the network would be able to help facilitate or manage to balance the load across different servers. And if in any way a network component is a bottleneck, what are the means to mitigate, overcome such bottlenecks and evade or avoid such data bottlenecks. And third is the power. When we are having lots of networking devices, also we spoke earlier about the middle boxes, which also are often present in large numbers in such data centers. So when they are powered up, our goal also is to ensure that they take or minimize the carbon footprint or be powered in a more efficient manner. And also whatever the heat that they are going to generate and the cooling mechanisms that need to be addressed for these specific devices be done appropriately. And often if there is no network load or no traffic that's coming, we would want to shut off such a device in terms of the network and bring it up only when there is a need for having access to such device. So power management at the whole of a data center level as well as at the networking level becomes crucial for better data center management. And third and most important is typically whenever there are failures, you would want to identify, detect such failures quickly and contain those failures. So localization, meaning trying to identify, detect and pinpoint where the failures have happened and isolate such failures from propagation is also a critical aspect when you look at lots of cyber threats that these data centers or in general the networks are open to. Hence, the containment of such failures also becomes a critical aspect. And especially when it comes to the networks, we are now talking about like links or the network links in the orders of several thousands to hundreds of thousands. And whenever one of the link fails, rerouting, ensuring that the updates are being done in a timely fashion and you avoid the root loops and you avoid the black holes becomes a critical concern when it comes to the networking devices. Also, when such failures are seen, especially lots of links flap, and whenever there is such a link flapping or temporary intermittent failures, you would want to operate and ensure that the services still function without having to see any downside of having one or several of such links to be down. That means we need to build the resiliency in the system which can enable us to overcome any of the intermittent failures and yet facilitate the service to run as if no failures have happened. And hence, building such a failure resiliency in terms of the data center networks becomes another crucial aspect. So, all these, in effect, are also the requirements, and at the same time, doing those for thousands of devices is also a major challenge. So, in this aspect, let us try to understand a bit on the data center costs in terms of where the network point of view it stands and what's the overall cost factors which data centers account to. So this was a study done early 2010, and what it showed was that the servers or the CPU, memory, and the disk components of a server machine in a data center that's hosted costs to roughly around 40 to 50% of the data center cost. And the power being the another important component that added to the cost, roughly around 20 to 25%. Well, the network added to around 15% roughly for the overall data center cost. And when we say network, that's basically the switches, the links, the transit links, the management of all of them. So you can see 15% is not a small component when we are talking about billions of dollars that you had to invest for bringing up the macro data centers. So it becomes important to manage these devices properly so that we are able to both reduce the capital expenses as well as operational expenses. And in this regard, we saw how NFV helps lower the capital expenses, and SDN with a centralized control helps lower the operational expenses, ensuring that you have a centralized control over all of these devices. Think of millions of such routers, millions of switches and routers that are being configured and controlled. You wouldn't have enough manpower to handle or manage these unless you centralize and handle them more efficiently. Thus, SDN and NFV, we can see that they have really played a great fit towards the data centers and also enabled to minimize these costs. And another important aspect is that when we think of servers or the networking components, every year there is an improvement, and the servers typically get better and better as we progress. And typically within 3 to 4 years, you would have to replace with a new server. So we would want to ensure that the amortization cost of the servers, that is to reclaim the amount of cost that we would have put, or whatever the cost that we put, how quickly does it zero out in terms of providing the value worth for the buck, is in terms of typically around 3 years. But when we look at the infrastructure as a whole, it takes a lot more time because you invest a lot more of the investments towards the infrastructure, and it takes around roughly 15-20 years to amortize the cost on the infrastructure. So what this tells us on the other side is that we are going to be upgrading our servers, upgrading our networking devices more often in a given data center. So these, when we are going to upgrade, it shouldn't take long time to provision and patch the updates or replace the hardware. Hence, whenever the new servers are purchased or new networking devices are upgraded, we need to ensure that we are able to patch them up, update with as quickly as possible without having to have longer provisioning time scales. This is also a crucial aspect which would add otherwise to the cost, and any downtime incurs a negative penalty for any servers. So hence we want to also ensure that we don't pay cost in these aspects. So the question now comes, like, what's so much different about data center networks? If not, like if we are already managing so many of the web servers, the file servers, data center networks, which way do they differ? And if we look back in this, we are talking about a huge networking infrastructure which is enabling the access to the servers from across the internet. And if we think of just the inside of a building where the data centers are housed, we would see that the links themselves are in the span of several hundreds, thousands of networking links and networking devices that we are operating with. Hence, this is basically a mini internet kind of a framework that we have to deal with, but all under one control, meaning we have the flexibility to weave how the network components should be connected. As data center owners, have the flexibility to decide how the servers would be connected to such networking infrastructure, what's the networking infrastructure we would want to build inside of the data center, and how we would want to enable connection to the outside world through the use of the routers and connect them with the internet. So these aspects typically were studied in the early 90s and by early 2000, late 90s and 2000s. Typical network topology in terms of what should be the way the network should be built if the data centers have to be scaled, and if the data centers have to be having the means to upgrade and add and scale the components within this data center. And Cisco recommended this 3-tier or a multi-tier architecture, and this multi-tier model has been the most common model that's been used in the enterprises today. And this design can cater to any of the web applications, database servers, various of the platforms in terms of what kind of servers we would want to deploy, heterogeneous mainframes, multiple of the rack servers, all of these could be constituted in this architecture or a topology as shown here. The data centers aspects, if we have to consider, what it shows at the topmost is the internet layer through which it facilitates connectivity for a data center to the external world. And to do that, at the boundary, we see what we call as these core routers. And these core routers are basically the bridge that facilitate us to connect to the external world and connect the underlying network infrastructure that we would want to view for our data center. So these are basically the topmost points for starting the data center fabric. By fabric, we mean what kind of a network topology, what's the link bandwidths, what kind of switches, what are the capabilities of each switches, all that a data center owner decides. And this is where the data center's layer 3 networking starts. And these core routers, which connect to the internet, inside the data center would connect to what we call as the aggregation routers. Or you can see that now we are spreading this network to multiple of the aggregation routers so that we are able to disaggregate the incoming traffic and channelize the traffic for particular operation, and also scale these aggregation routers as and how we want to scale the data centers. And both the L3 core routers and L3 aggregation routers facilitate what we call as the data center's layer 3 mechanism. And this layer essentially is a gateway for connecting inside and outside worlds. So for all the devices that are within the data center, the aggregation routers act as the gateway to connect to the outside world, while the core routers act as the means to connect the external entity outside of the internet to the entity that is inside of the network. And this aggregation layer with many excess layers that can be linked further down to provide what we call as the layer 2 network within the data center. And this layer 2 network is much more critical in the sense of scaling up of the resources that we would want to do, while be it the deployment of the middle boxes, be it the deployment of the switches or the server racks that we spoke about earlier in terms of how we want to scale. And at this layer 2, all this S marked as S are the switches would enable us to operate in the layer 2 domain, meaning we can operate and ensure the connectivity amongst all of these internal devices just at a layer 2 as if it's a single LAN. And we could even isolate them by the use of VLANs and ensure connectivity accordingly. But in terms of connectivity, we could have a simple layer 2 connectivity rather than trying to do layer 3 connectivity through the aggregation routers. What this also means is if I have any of the server racks underneath, we should be able to facilitate communication just at the layer 2 without the need to go to the aggregation routers. We would need to go to the aggregation routers only if we have to connect outside of our domain and use the aggregation routers as gateways to facilitate connection to the outside world. And this mode plays a critical role in meeting several of the requirements, such as like if we want to upgrade the hardwares or switches, we can do them much more easily and provide better bandwidth, upgrade the infrastructure resources within the layer 2 space. And typically this access layer is the first oversubscription point in terms of like how much should be the link bandwidths that we would want to support at each of the layers can be defined with respect to each layer in terms of what's the traffic that we expect to move when it is between the rack, when it is within the rack, and across the rack or in between the racks. And think of two racks trying to communicate with each other, then the connection has to go through these switches, like what we are showing at least at the bottom half, the access switches to connect two nodes that are on different racks. And likewise, we may have to go through the other tier, the higher tier of the switches to connect to the racks in a different region. So we can scale these resources, and we can also set up what should be each of the link bandwidths that need to be set up. And this is the most typical network infrastructure that was being used in the early 2000s for the enterprise data centers. And then most of the links used to be like a 10 gigabit Ethernet channels that used to enable traffic communications across these devices. So let us now look at the components that we just discussed in such a network topological architecture in more detail. So at the bottom, what we typically see is a rack, and each rack hosts a bunch of servers. Like we said earlier, a 42U rack could host around 42 of the single U, 1U racks. But if there are 2U or 4U devices, the number would go down accordingly. And typically we expect around 20 to 40 servers within each rack. And at each rack, or what we call as a server rack, there would be one switch that is being set, which is enabling connection amongst all of the servers that are present within each rack, so that if there are two servers, they would be able to communicate within themselves using this switch that is sitting on top, which we call as the top of the rack switch. And this would be one switch per rack, and a typical bandwidth or the link facilitated through this switch is around 4200 gigabits Ethernet. So if two devices that are on this rack want to communicate with each other, they would get around 100 gigabits per link bandwidth to ensure that they can communicate with each other thoroughly. And we may have like 40 of them each connected through this switch, each getting around 4200 gigabits links connecting them. And these become the units of scale at the lowermost end, where if we are speaking of hosting around hundreds or thousands of servers, so if we speak around 1000 servers, then we would need at least 50 of such racks so that you are able to host 100 servers, considering approximately 20 servers per rack. And if we are speaking of order more, like 10,000s, then accordingly the number of server racks that we would want to deploy would increase. And as these server racks increase, now if we want to communicate amongst these racks, then this is facilitated through what we call as a tier 2 switch that sits and connects with multiple of these racks. So we can see that this tier 2 switch now is able to connect to around multiple of these, approximately consider 16 top of the rack switches can be connected through these tier 2 switch. And now we can enable connections to ensure that we can have communication between 1 and 3 or 2 and 4 to go through these tier 2 switches and facilitate this connection. Now the question comes, what should be the bandwidth for the links of this tier 2 that are having the down links that are connecting with each of these top of the racks? Should they be again 40 to 100 gigabits or should they be more? Right? So this is where the principle of oversubscription comes. And if we say that each of the links that are down here are 40 gigabits and each of the links that are connecting to this tier 2 is also 40 gigabits, then we basically have the same bandwidth. But in terms of the communication, now we can have, if we had just two of these servers, each between 1 and 2, it would get 40 gigabits per second. And between 1 and 3, it would also get 40 gigabits per second that it would communicate. But now this communication can, as you scale the racks, it is going to be accordingly shrinking in terms of what bandwidth they would get when all of them would go. And this results in what we say, the more you add, the subscription becomes much more on those links, which is much more than the thing that you could basically support. So if all of these 1 and 3 also wants to communicate and 2 and 4 also want to communicate, you have requirement of 80 gigabits per second bandwidth. But since these links are only 40 gigabits, now you have oversubscribed it by 2. So 1:2. And likewise, if you increase the number, you would see that it would start dropping. And that's how the oversubscription typically happens. And if you want to avoid, then we would want each of these links at this point to be 80 gigabits per second so that they're able to support the traffic. And that's where we will see that there is a interplay of how you want to build the links and what kind of bandwidth that they should be supporting for each of the connections. And like we said, we are not confined to a small set of racks. We are talking about hundreds to thousands of such racks. So what this would mean is we would be replicating such a unit multiple of the times to ensure that we are able to meet and scale out the required resources. And when we scale out, now if we want to interconnect and communicate between this, we need another mechanism. And that again, we can think on the same lines to be facilitated through the tier 1 switches, wherein you have a tier 2 switch connect to this tier 1 switch, and this tier 1 switch would then connect to every other tier 2 switch in the network. So all the tier 2 switches are now connected with the tier 1 switches and ensure that I can communicate amongst any of these through the pair of tier 1 and tier 2 switches that I want to go. So if I had 1, 2 and I say I have 10 and 11, if one has to communicate with a device 10, it would go through the switch and then it has an option to go either to this switch and then come here, or it has an option to go here and then connect to the devices 10 and 11. So likewise, now we are trying to build lots of possible routes through which we are able to connect the two ends of these. And typically what we call this instance of a scale as a pod, which constitutes of multiple of such racks connected with a tier 2 switch as a scaling unit that would then be connected to a tier 1 switch. And again, we can scale these tier 1 switch, and if you consider 16 of such things, now we have 16 cross 16 cross 40 of such servers that we can basically connect in this network. And again, as this network has to connect to the outside world, we would need these border routers. And again, these border routers can again be layered, as we saw, as either the core and aggregation routers or simply the core routers that enable us to connect outside. So this is a common means of setting up the data center network elements. And we spoke about this top of the rack switch, which enables us as a module for each rack to connect to the tier 2 switches, and tier 2 switch as an entity that would allow us to scale at a level of pod, and tier 1 switch allows us to communicate amongst multiple of such pods, and the border routers facilitate to connect to the outside world, and thus we can see that we can operate with scales of tier 2, tier 1 switches to ensure that we can connect each and every entity within the data center and also with the outside world. And also, when we speak of this core routers, again, the bandwidth for these links, should they be again 40 gigabits or 100 gigabits? How should we determine? This becomes a concern, and that's where many of the different kinds of topologies were brought to see which one would fit better. And we can also observe another aspect, like when we want to communicate within a rack, we have one hop devices going through just the switch. And when we want to communicate within a pod, we have two hops, that is one top of the rack switch, then going to the tier 2 switch and then coming back to the top of the rack switch for that corresponding destination, so that you have at least two hops before you connect to the end host. And when we have multiple of these pods that want to connect, we are having one more hop of two hops that is being added by the tier 1 switches to go what is the source tier 1 switch through which you can reach the other end. So you have one top of the rack going to one of the tier 2, then going to tier 1, then coming back to tier 2, and then to the corresponding top of the rack, and then to the device. So you can see that in terms of latency, when we increase or scale out in this fashion, we would also incur additional excess latency and additional hops through which we have to navigate. And this is pretty common when we consider this kind of a model. And it is not just that we have top of the rack as a means to connect. There were also other models that were identified and see which would suit how. And to put it, like what we have seen as a top of the rack, each rack has a switch as a top element, and all of these servers would connect with this switch first, and then this is the one that connects to the aggregation switch or the tier 2 switch that we just saw. So this is also called as in-rack design, and in this, the network access switch is always placed at the top of the server, and all the servers in the rack directly connect to this network access switch. Also, although the top here means at the rack, but it's not necessary that you place the switch just at the top. It becomes like simpler as a convention to put it, but you could as well put a switch somewhere in between the rack. There is no such binding that it has to be just at the top. But the convention that is being used is each rack hosts a switch, and this switch is then connecting with the aggregation switch. And what you can see now, like as I scale my racks, I need one switch to be purchased and set up. This will be, in terms of cost, it would be expensive, and in terms of management also, we need to handle a lot more of the switches. So the alternatives were thought, and two of the models were proposed. One is called end of the row, wherein when you connect each of these racks, the racks need not have any switch which interconnects them. Rather, I would bypass this top of the rack switch and connect all of these devices directly to the aggregation switch. So what that means is you will have lots of wires that would go from each of the rack and connect to the aggregation switch, which might be placed at the end of the row, so that you have one place where the aggregation switches are placed and you are cabling all of the racks server cables to connect to that aggregation switch. So what this means is now there is a direct connection for each server with respect to the aggregation switch. And now if any of these devices, whether it is inside of the rack or whether it is across the rack, if they have to connect, they just have one hop, that is the aggregation switch. So you have in essence eliminated the additional top of the rack switch as a hop to facilitate this communication. And that's also eliminated the need for these in-rack switches, saving a lot on the cost. But this has its own consequences when we think of like now we are cabling, we are sending a lot of these wires and making these connections a lot more on the aggregation switch. So the number of ports that you would need for the aggregation switch, you can see here we needed just around 3 ports for connecting all the racks. Now you would need as many as if there are 10 of these, then you would need 30 of these ports on the aggregation switch. That's also an expensive affair in terms of setting up. And also wiring, now like all of these devices were wired just inside. Now you are moving the wiring all the way up to the other end. So this also adds to the cost on how you would wire and what's the in length that you would use to connect these wires. And again, like this is again a convention when we say end of the row being placed at the very last element in the row, but not necessarily that we have to follow this end of the row convention. This could also be the case where we would seat this somewhere in between and switch the rack out. So that would become essentially what we call as the middle of the row. And this would help avoid the cable length so that either side of the rows can be connected to this middle of the row. And this is exactly the same as what we spoke of this end of the row model. And this is another variant that's also followed, but in a very less of the cases, while most of the cases typically use top of the racks. So if we consider in terms of how these would compare, if we think of network deployment, in the TOR design, you would need one switch per rack as an additional entity. While in the end of the rack design, all the switches centrally residing in 1 to 2 racks of the same row. That means you only have the aggregation switches that are being placed in one row, and you have eliminated the need for one switch per rack. But if you look at the modularity that you get with top of the rack design, each rack is a separate entity that can communicate amongst themselves. And if I want to isolate them from connection with any other entities, I can just take out the connections that connects the top of the rack switch to the aggregation switch, and the entire entity becomes contained in its own. And I can even move this rack around. So it becomes very modular in terms of treating each rack as a separate entity that can be connected, updated, and done. But this end of the rack design, the module rack works as a group because now you are connecting all of these devices to the aggregation switch. So, and if I have to take out one of the device, I have, or n devices within a rack, I have to basically cut off the links with respect to the aggregation switch. And if we consider in terms of the required devices, yes, TOR has a higher count because you need switch per rack, while EOR has a lower count. That also means that because now you have lowered the devices, the utilization of each of the links would be maximized because the connections would be direct through the server to the end of the rack. So effective utilization of the switches is more in the end of the rack design as opposed to the top of the rack design. But top of the rack, although it provides underutilization, it's in a way also giving ample bandwidth to change within a rack in terms of how you want to scale the resources. But for this scenario, until aggregation devices are upgraded, there is no change in the bandwidth for a given end of the row model to communicate. And in terms of power and cooling, we would also see that there is a lot more higher power consumption because of additional devices that are being put in each of the rack in the TOR design as opposed to end of the rack. And this power also means you also need greater amount of energy for cooling. But when we look at just the layer 2 communication, the best part about this top of the rack is because we are contained within a rack and communications can happen much more easily. So the layer 2 communications that happen within a rack is always more efficient in top of the rack as opposed to end of the rack devices. Although the number of hops are lower, the means for layer 2 data traffic to move is much more simpler in the end of the top of the rack design as opposed to the end of the rack. And also the expansion, like we said, because it's much more rack has an independent entity that can be plugged in, plugged out, and the only way to scale is through adding one more link on the aggregation. But now, on the end of the rack design, the expansion is a lot more difficult, because if you have to add one new rack, in the TOR design, it is equivalent to saying adding one switch and adding one port extra on the aggregation switch. But in the end of the rack, you need to provision again for multiple of the ports on the aggregation switch. And this is where we see that end of the rack has some benefits as well as some drawbacks when it comes to the utility and setup. And most preferred, like I said, is typically this top of the rack design.